So I have a very unoriginal title, Remarks on Relational Physics. And I guess that's what it'll be. Here's what I submitted as an abstract. I said I was going to discuss classical and quantum relational physics, but it'll be mainly quantum. And relational physics, of course, involves relational space, and I mean also include relational time. I'm going to begin by discussing what it is. What is relational space, relational time, relational physics? By the way, can everybody hear me?
Yes.
Yes. Yes.
Yes, I can.
But what is it? What does it point? Why should you care about it? Why do I care about it? And what we can learn from it. And I particularly want to focus on freedom, gauge, what would naturally be called gauge freedom, and the concomitant objectivity or subjectivity are various things we take to be fundamental in physics. There are implications for probability and non-normalizability of the quantum state. Not sure how much time I'm going to have to get into that. What I'm going to describe is based on work with Detlef Durr, my dear departed colleague, and Nino Zanghi, who is not departed, but with us. And the work was inspired by work of Julian Barber and Bruno Bertotti. I'm going to convey very, very few mathematical details. Maybe very few details of any sort. Details, mathematical and otherwise, can be found in my paper with Detlef and Nino from several years ago, Quantum Motion on Shape Space, and the gauge-dependent emergence of dynamics and probability in absolute space and time. There's a sense in which you could also say that concerns the emergence of absolute space and time. Okay. Begin with what is relational space? In simple terms, it's what you get when you say, look, suppose you have a stuff in space. Let's think I'm going to be focusing throughout on particle ontology. So you've got particles in space, and you've got configurations of particles. Suppose you say that the overall position of the configuration is not relevant. It's not even physical. So if you translate everything by the same amount in the same direction, you don't regard that as a real change, a physical change. Suppose you say the same thing for orientation. So you rotate everything uniformly, not a physical change, you say. Suppose you also say that overall size, do a uniform rescaling. Overall size is not relevant. Well, then what's left is a shape. And you say that's really what physics is fundamentally about. And if that's what physics is fundamentally about for relational space, if that's what physics is fundamentally about, then you would like to formulate physics in fundamental terms. In any case, the resulting space you get when you quotient out by the symmetries that I mentioned is shape space, which is to be contrasted with the space you began with, absolute configuration space. The fundamental space, the point of view here is that the fundamental space is shape space. To have a simple example, and probably was mentioned in earlier talks, but it's one of the simplest non-trivial examples. Suppose you have 3 particles in physical space. Once you quotient out by all the symmetries I mentioned, so orientation, position, and size doesn't matter, you're just left with similar triangles characterized by 2 numbers of 2 of the 3 angles. The shape of the triangle, similar triangles. 2-dimensional space. Whereas you started with a good deal higher dimensional space, 3 particles, a 9-dimensional space. 3 particles in 3 dimensions. Okay, that's relational space. What is relational time? Well, it's another word for, you might call it quantitative time, qualitative time, as opposed to quantitative time, or non-metrical time. So that if you're dealing with relational time, what you say is, well, what I really have, if I have given some configuration space, say shape space, but it could be any configuration space, but you can consider time relational. What does that mean? It means, well, things will change with time, so you got a trajectory, but trajectory just means a path in configuration space, a continuous sequence, where there's no fact of the matter as to how fast or how slow you're going along the path. So instead of it, what we usually do with, which involves parametrized trajectories, so each point along the trajectory is assigned a time, you don't assign a time. It's unparameterized trajectories, just paths in configuration space. And you say that's what's physical. Geometrical paths in configuration space. What is relational physics? Relational physics is what you get when you use only relational time and relational space. It's a combination of relational time and relational space and physics. Let me make here's one remark, the difference between relational and relativistic. The words are a little similar, but they have rather different meanings. In both cases, relational and relativistic, and here you should think mainly of relational time, but relational space as well, but it's really the contrast is with relational time and relativistic. With relational time, as well as with relativistic physics, you do not have simultaneity. But the absence of simultaneity for the 2 cases, relational time versus relativistic time, is very different. In the case of relativistic time, the absence of simultaneity is actual. There is no actual now, no special now. The reality is 4-dimensional in some sense. No preferred now. And that's relativistic time. In relational time, with relational space, you have configurations, relational configurations, shapes. These are well defined at a given time, and they change with time. If time is relational, they change with a non-metrical time. But they do change. So there is a well-defined notion of now. The absence of simultaneity is hypothetical. Suppose you give 2 different possible, and think of different initial conditions, whatever that means from a relational time point of view, 2 different histories of the universe with relational time. That means 2 different paths in configuration space, geometrical paths. Doesn't mean anything from a fundamental point of view to ask about, to compare the configurations at the same time. There is no such thing as the same time for different possible histories, because the histories are not labeled with a time parameter. They're unparameterized histories. Okay. Now, what is the relationship between relational space and relational time? It's a very harmonious one. It's of course true that if you like relational time, you're going to be more, it'll be more likely to like relational space. If you like relational space, you'll be more likely to like relational time. But if you want to extract the consequences for how things appear to us from the point of view of relational space, the most interesting conclusions can be drawn if you also regard time as relational. And this is particularly relevant to the kinds of gauge freedom that I want to focus on later in the talk. What's the point of doing relational stuff? Why go relational at all? Why bother? Both from a general point of view or from my own personal point of view, why did I get involved in it? Well, first of all, whether you think relationality is fundamental, shape space is fundamental or not, I think it's pretty clear that from the observational point of view, if two configurations which are related by one of the symmetries, and these are, think of them as configurations of the entire universe. These symmetries are, the changes related by these symmetries are not going to, corresponding to these symmetries, are not going to be observational, nor will speeding up or slowing down the whole universe, the universe as well. It's irrelevant to observation. The observation has to do with correlations between different parts of the universe. We don't have access to any clock outside the universe. So if you say what's fundamental must be what's observational, you should go relational. I think that's too extreme. What's fundamental could well transcend what's observable. But nonetheless, it seems very, if distinctions, things that differ only by the symmetries that define shape space, the things that differ in such a way, if those differences are not observational, it seems reasonable to explore the possibility that they aren't real physical differences at all. They're not fundamental, they're not physical. So it seems natural to explore the possibility of formulating physics in those terms, in what seem like natural posits as fundamental terms for physics. And then what got me probably thinking about it more than anything else was certain issues in quantum mechanics. And by quantum mechanics, I really have in mind Bohmian mechanics, although maybe you could say more generally. I saw Lev was there, okay, still there. So when I think of quantum mechanics, I really do think, I mean Bohmian mechanics. The other versions of quantum mechanics are for me simply too implausible or too incoherent to be taken seriously. I know it's kind of eccentric to insist on it, but that's just how it seems to me. Quantum mechanics is Bohmian mechanics, or some Bohmian kind of thing. In any case, Bohmian mechanics fits very naturally with shape space ideas. But I should say a few words then about Bohmian mechanics before continuing with other stuff. Why do you need Bohmian mechanics? What's the problem with quantum mechanics? There's a huge number of difficulties, problems. One can't be negative enough about it, I would say. But I think what Bell said concerning orthodox quantum theory is pretty much on target. Maybe too generous, but pretty much on target. Namely that it's unprofessionally vague and ambiguous. It's not at all clear what it's about. Here's Bohmian mechanics. With Bohmian mechanics, what have you got? You've got the usual wave function of quantum mechanics, the function of the configuration, Q1 through Qn, configuration of n particles. But in addition to the wave function, you've got the particles themselves taken seriously. Taken seriously means they have actual positions, Q1 through Qn. So you add something pretty basic to the ontology. Serious particles. But how do these things evolve? Well, the wave function evolves in the usual way according to Schrodinger's equation. And the particles evolve according to what I've written in blue, according to what's called the guiding equation, which is kind of the obvious evolution equation for the configuration once you know Schrodinger's equation. This equation could be simplified for particles without spin. If you have spinless particles, and psi is just a scalar, and the psi star cancels from the numerator and the denominator, and we have grad psi over psi. For particles with spin, you need to have this kind of form, which is good to have anyway, because this makes it manifest that the velocity is j over rho, which will be an obvious. So if you wanted to guess what the velocity should be, j over rho, that's a pretty obvious guess given what j is classically, rho times v. This, in the case of scalar wave functions, so the grad psi of psi just amounts to grad s, where s is usual phase in the polar decomposition of the wave function. And this is just remarking from the early quantum de Broglie relation. If you ask what that really means, it more or less naturally suggests the time evolution for psi, Schrodinger's equation. It naturally, and it almost even more simply yields the guiding equation, time evolution for Q. I won't go into that. Here is the picture people have seen many times of what the Bohmian trajectories are like for the two-slit experiment, where you see interference fringes forming because of the interference between the part of the wave function going through the upper slit and the part going through the lower slit. Here's a nice quote from Bell about it, which I think I will skip. What do you get from Bohmian mechanics? Everything you could want. Familiar macroscopic reality, quantum randomness naturally emerges. Full quantum randomness, even with absolute uncertainty that can't be overcome. The role of operators as observables. You get the good notion of the wave function of a subsystem, which collapses. So you get collapse of the wave function, and you have a clear indication, a clear quantum non-locality. It was because Bell was studying Bohmian mechanics that he led to his proof that quantum non-locality is unavoidable. This is about an important property of the psi squared distribution of equivariance, but I don't think I have time to get into that. The bottom line is that Bohmian mechanics works. Bohmian mechanics is really simple, and Bohmian mechanics is kind of obvious. Amazingly so, given the resistance to it. In fact, you have this, I like this awful acronym for it. It is the obvious, given Schrodinger's equation, Bohmian mechanics is the obvious ontology, particles with positions, evolving the obvious way. That's all it is. I do want to distinguish between Bohmian mechanics and a Bohmian approach. Bohmian mechanics involves a particle ontology. We've got particles. Bohmian approach, there's going to be some clear primitive ontology, basic fundamental of the ontology, describing matter in space, but it might not be a particle ontology. It could be a field ontology, it could be any, whatever, various possibilities. However, if it's a quantum theory, there'll be a state vector psi in Hilbert space. It'll evolve of some kind of Schrodinger, according to some kind of Schrodinger equation, and will guide the behavior of the particles, maybe by stochastic laws. And it will also govern probabilities in ways described in the second bullet, which I don't think I want to get into right now. And again, as I indicated before, for scalar wave functions, when you decompose the scalar wave function in polar form to define the phase S, you get a very simple equation for the guiding equation. The velocity is just the gradient of s. Gradient motion. Once you see that, you easily get quantization for Bohmian mechanics, Bohmian theory on a Riemannian manifold. You need a Schrodinger equation. So you need a Laplacian. If you have a Riemannian manifold with a metric G, you have a Laplacian that's given by G, the Laplace-Beltrami operator. And if there's some function on potential, you've got Schrodinger's equation, nothing really to do. It's just, you get it straight away. And as far as the guiding equation is concerned, if you have some wave function with phase S, set the one satisfying Schrodinger's equation, you need a gradient, as I had in the previous slide, gradient S. And the natural gradient or Riemannian manifold is the gradient given by the metric, grad G. So Bohmian mechanics on a Riemannian manifold is immediate. And at the end of the day, once again, you have an equation of the form, a first order equation of motion for a configuration. Configuration is given by some velocity vector field. The velocity vector field is generated by psi, comes from psi, it's a function of psi. So that's all very fine and good, but there's some puzzles. I wouldn't call them difficulties, but some puzzles, at least they were puzzles for me, associated with Bohmian mechanics. One puzzle concerned the wave function of the universe and entropy. In Bohmian, in one of my first papers with Detlef and Nino about this subject, we claimed that because quantum systems, Bohmian systems, are always in quantum equilibrium relative to the wave function. It's the wave function which is not in equilibrium. So that thermodynamic equilibrium corresponds to a wave function not being an equilibrium wave function. And the entropy should therefore correspond to the entropy of the wave associated with the wave function. But the wave function of the universe typically doesn't change with time. So if the entropy is determined by the wave function, the entropy doesn't change with time. And that's pretty bad for our universe, which is somehow not an equilibrium, and entropy is increasing. So there's a puzzle there, there's a problem there. Things aren't so great. And once you actually are thinking about the wave function of the universe, the wave function of the universe is typically not normalizable. The psi squared for the wave function of the universe, the probability density for the wave function universe is not a probability density. Since the total measure is infinite. So how do you even deal with probabilities in such a case? It seems like a disaster. And then a question of a very somewhat different spirit, paraphrasing, maybe quoting Robbie. Okay, you've got this very nice theory involving wave functions. Who ordered that? Why should you have wave functions involved in governing how things move? Who ordered that? That's particularly puzzling if you think about what kind of thing you're normally dealing with, what kind of wave function, what kind of object the wave function is in quantum mechanics. It's not an ordinary field on physical space. It's a field on configuration space. It's a pretty strange kind of object. So you may have a well-defined theory, Bohmian mechanics, perfectly well-defined, but still puzzling. What is this thing, this wave function? Why should you have a theory of this form at all? So I asked the question, why? And that's the question which is to be distinguished from the question of what. What is quantum mechanics, I think, is well answered by Bohmian mechanics. But why is not well answered by Bohmian. Why should you have something like Bohmian mechanics involving a wave function at all? I do, however, want to contrast what often is done in foundations of quantum mechanics, where the question why is asked before the question what is addressed. You ask, oh, what principles should lead to quantum mechanics? You have this sort of strange theory. Let's think of some principles, some nice, compelling principles that lead to it. Oh, well, that's all fine and good. But at the end of the day, if what you end up with after invoking those principles is still unprofessionally vague and ambiguous, so much so you still don't know what it's saying, then your question of why was premature. Your question of why should only be asked once you already arrived at a reasonable answer to the question what. And what I believe is the best answer to the question why is that the wave function is basically should be thought of as a, let me know if there's some trouble, because I've just noticed my internet connection is unstable. Does everybody hear me?
Yes.
Yeah, it's still fine.
The wave function should be thought of as law. By wave function, I mean here the mother of all wave functions, the wave function of the universe. That's the only one you really need to formulate the theory in a fundamental way. That should be thought of as a law. It's an object which, in terms of which it's convenient to write down the right-hand side of the guiding.
Now, did we lose Shelley?
Yes, I think he's gone.
Yeah, yes, we did.
I think he's here, but muted.
What?
At least I see his image on the gallery, but it's muted.
Shelley, you are muted somehow.
Now you can hear me?
Yes.
Yeah.
Can you see the share screen?
No.
Nope.
No.
Try again. Can you see the
Okay.
share screen?
Yeah,
Yes.
great. We are back.
Wave function is law? Good.
Yes.
So to QDT is V psi of Q. I had that a bit ago. That's just, suppose you had the idea. So let's see. Let's find some compelling principle which will lead you to an equation of motion. The QDT equals something, and so that it just simply turns out that that something can be naturally expressed in terms of a wave function satisfying a nice equation, like Schrodinger's, like a time-independent Schrodinger's equation. So I'm repeating myself here. So you have the QDT V psi of Q, and for the wave function to be a law, V psi should be a simple enough function of Q. The law should be simple. That's what, if I had an answer to some compelling reason which would give me a motion on a configuration space of such a form, of such a character, I would think I understand where quantum mechanics is coming from. I don't have that. And something that might help understand how physics can be put in, how the emotion can be expressed in such a form is the flexibility and gauge freedom afforded by relational physics. Again, what the goal is to arrive from the physical or fundamental dynamics at one that is given by a V psi for some sufficiently simple psi, or failing that, one that satisfies a time-independent Schrodinger's equation, like H psi equals 0, for some sufficiently simple H. This quantum form of the theory would be a kind of Kantian component of the theory. It's not fundamental. It's just a choice we make for a convenient way of expressing the law would be of a quantum form. So I want to say a little more precisely what shape space is. You have absolute configuration space, and let's contrast that with shape space. The similarity group is the group I described before, just generated by translations, 3 independent translations, rotations, 3 independent rotations, and scalings, 1 scaling. So a group of 7 dimensions. So when you take absolute configuration space, script to Q, quotient out by the similarity group I just mentioned, and look at equivalence classes. So you say 2 configurations which are related by a symmetry are equivalent. Look at the equivalence classes. The equivalence classes are the shapes forming shape space. That is shape space. Here's a simple pictorial representation of it, much too simple in a sense, where the shape space is one-dimensional, will typically be quite high-dimensional if there are a lot of particles. And then the fibers over the shape, over the shapes on the bottom. Fiber over shape, that's the set of all absolute configurations which are equivalent to a particular shape obtained by applying the symmetries. It's not, of course, one-dimensional, it's a seven-dimensional. The fibers are seven-dimensional matter. This, in fact, is a nice fiber bundle. In fact, I didn't have a good feeling for what fiber bundles really were until I started thinking about shape space. So in the case of three particles, where the triangle, we were dealing with the shapes of triangles, and then the different fibers or different orientations or sizes of the same similar triangle. The fibers, the tangent space to a fiber's of possible directions are either along a fiber or orthogonal to fibers. There's a horizontal direction and a perpendicular direction, and that plays an important role in defining, well, let's look at point 4 here. In order to define Bohmian mechanics or classical mechanics on shape space, you're going to need to have be able to do analysis on shape space. You're going to need to have a metric on shape space so that shape space become a Riemannian manifold. And if you have a Riemannian manifold, you can have free motion, geodesic motion, for the classical case, and as I indicated before, Bohmian motion on that Riemannian manifold. So you need a metric, a natural metric on shape space. And a natural metric on shape space, it can be obtained by, in a sort of canonical way, by having a Riemannian metric G, which is invariant on absolute, an invariant, sim-invariant Riemannian metric on absolute configuration space. How do you get such a thing? Well, Euclidean metric is sim-invariant. It is invariant under translations and rotations. It is, however, not invariant under scalings. To compensate for the changes that happen under scalings, look at the last bullet. You multiply the Euclidean metric by a function f, which is an Euclidean invariant function, which is homogeneous of degree -2, just the right homogeneity to cancel out changes due to scaling. And this way, multiplying the Euclidean metric by this, what we call the conformal factor, you get a sim-invariant metric G. And from a sim-invariant metric G, you easily get an invariant GB, a natural metric on shape space. How so? Basically by just going horizontal, given a configuration Q0 and a neighboring configuration Q0 plus DQ0 in the base and Q0 in shape space. You pick any point corresponding lift of Q0 into its fiber, into its equivalence class, and then lift DQ0 from the base to a horizontal, perform the unique horizontal lift to take you to a different point in a neighboring fiber. And the distance between Q0 and Q0 plus DQ0 is then just the perpendicular distance so obtained in absolute configuration space, defined using the invariant metric G on absolute configuration space. Because that metric is invariant, this prescription is unambiguous and gives you a well-defined metric, Riemannian metric on absolute configuration space. Here are some examples of conformal factors, sort of very natural things you could write down. I shall not dwell on that at all. Let me indicate why is this Riemannian metric that we obtained called GB? Why the B? G can stand for base. It could also stand for Barbour and Bertocci. It's the metric you obtain by best matching. Maybe there are other reasons we called it GB. There's some extremely nice mathematics associated with the metric on shape space, Berry phase, Hopf vibration, spin 1/2, Bloch sphere. But in any case, as I mentioned already, free motion on shape space, both classical and quantum, is a piece of cake. The Riemannian metric gives you the geodesics for free motion. In the classical case, the Laplace-Beltrami operator, delta B, associated with GB, and the Nabla, the gradient operator associated with GB, gives you immediately Bohmian mechanics on that. The Riemannian manifold, that is shape space, the Riemannian manifold defined by GB. It's Riemannian metric, it's natural metric defined arising from the conformal factor. Now, so that's fairly simple. The hard work, at least for us, basically in the quantum case, involved the transition from the fundamental level of shape space to what I'm calling here the human level of absolute configuration space. Human level, because that's the description we use. Even if shape space is fundamental, we humans don't typically write things in terms of, formulate things in terms of shape space. That doesn't quite come so naturally, even if it is in some deeper sense much more fundamental and natural. So the level of, in terms of which physics has traditionally been done for good human reasons, and maybe probably many others, I call that the human level, the level of absolute configuration space. That's a certain emergent level because it's not fundamental. How we describe things on that level is imposed by us. It is human and it's based on our choices of description. And that's why I consider it a kind of Kantian component of physical theory, which it turns out to be rather large, this Kantian component of physical theory. So much of what we took as fundamental from the relational point of view is not at all fundamental, but imposed by us by appropriate choice of gauge. One thing that emerges is interaction. If you start with the classical case, free motion in space, and go into what's called the Newton gauge, you end up with forces acting in the Newton gauge when you do the Newton gauge lift to absolute configuration space. In the quantum case, the corresponding gauge is the Schrodinger gauge, where again you get interactions emerging from the free motion on shapes, free Bohmian motion on shape space. So you have this, because of the flexibility you have, different possibilities of choices of gauges, different choices correspond to different forms of interaction. I want to go into more detail about the sources of this gauge freedom. Keep this picture in mind. In the classical case, there are two sources of freedom, gauge freedom. Suppose you have some motion in the high dimensional Q0. So you have some path. Then an equivalent motion in absolute configuration space would just be a lift of that path. So that each point in Q0, each shape is lifted to a configuration which projects to that shape. Now, there are many ways of doing the lifting. Suppose a path which consider a path that say somehow starts, or think of a particular point Q0 on the path. It can be lifted in a fairly arbitrary way to a configuration Q in the fiber above the path. Now, go along the path in shape space. One natural way to lift it is to always proceed horizontally. So that's what I refer to as the freedom of lifting. You could lift horizontally, or you could lift in a non-horizontal way. And the way to lift in a non-horizontal way is much larger dimensional than indicated here, because the fibers are not one-dimensional, they're seven-dimensional. So there are lots of choices you can make about how to lift in a non-horizontal way, as shown by the slanty arrow. But in addition to simply lifting in one way or another, horizontally is sort of a natural kind of thing to do. You can parametrize the path. If I use a time parameter associated with a geodesic parameter, distance, I might want to make a random time change. And in fact, I might need to make a random time change, which is perfectly reasonable from a relational point of view, because there's nothing fundamental about the time parameter. Just the geometrical path is fundamental. So those are the two sources of gauge of freedom in the classical case. In the quantum case, you do have the same two sources of freedom, naturally enough, but there's an additional source of freedom. Freedom in the choice of the wave function that guides the Bohmian motion. If you have one wave function and you just lift it from absolute configuration space to get a wave function which is constant on fibers, you might want to change that wave function in a variety of ways. And as long as you change that wave function simply by multiplying it by another function phi, which is real, this will have no effect on the phase S. It will not affect the Bohm motion. So you'll get an equivalent dynamics and hence an equivalent theory. So there's lots of freedom of how you choose your wave function. So in the classical case, what are the gauges? I'll just mention three possibilities. How much more time do I have?
Is 10 minutes okay?
That's fine, more than enough, I suspect.
Okay, great.
The classical, the first gauge is the gauge I first mentioned. When you lift, you use a horizontal lift, geometrically, naturally, and that's an invariant thing to do. So that's called not just the horizontal gauge or the invariant gauge. And lifting horizontally means that the motion will be such that the total momentum is zero, the angular momentum is zero, and the relational momentum is zero. That's automatic. That's the horizontal gauge, the invariant gauge. And then the motion you get in that gauge from geometric lift of the geodesic flow will not correspond in a terribly familiar way yet to Newtonian motion. To get Newtonian motion, you have to parametrize, reparametrize, make a time change in such a way that the velocity is slowed up or speeded up or slowed down so that the total energy remains zero. If you do that, you get what's called that's the time change freedom that you have. When you go to that, when you do that, you get what's the Newton gauge, where you have Newtonian motion with the potential, with force arising from potential, which happens to be minus the conformal factor. Another kind of gauge which could be useful, I think this is something that mentioned by Julian Bertotti, I think, is what you might call the expansion gauge. A gauge in which you don't do a horizontal lift, but you have a uniform, an appropriate expansion of configurations taking place. In the horizontal gauge, the overall size doesn't change. The relational momentum is zero. The expansion means configuration expands. Now, why would you might want to do that? Because that might simplify the gravitational forces that you have so that they become more familiar looking when you do that expansion. And that would be provide a rather striking picture of why we think the universe is expanding. So those are at least three possible gauges you could talk about classically. In the quantum case, I mentioned four gauges. One gauge, the two gauge, the three gauge, and the Schrodinger gauge. Nino, do you remember what we called them? One gauge? That's very unoriginal. One gauge, two gauge, three gauge. But in any case, that's what we ended up with. Then
I think we call it that way, yeah. One gauge.
Why, what, Nino?
I think we call it in that way, one gauge, two gauge.
Yeah, but that is after giving up other choices. Maybe. Is
Yeah,
that-
I
we just
forgot.
couldn't- We couldn't think of anything better or what?
I don't remember, Shelley. I just don't
Okay,
remember.
okay. In any case, so in the one gauge, here's what you, here's this. In terms of starting with the Bohmian, free Bohmian dynamics on shape space, which will involve the Laplacian on shape space. The one gauge is what you first arrive at. The two gauge is what you arrive at from the one gauge. The three gauge is what you arrive at from the two gauge. And the Schrodinger gauge is what you arrive at from the three gauge. In the one gauge, how do you get at the one gauge? You just, in the one gauge, you have a wave function on absolute configuration psi1 hat, an H1, Hamiltonian H1, a potential V1, which happens to be 0, and the Hamiltonian involves the velocity delta 1. Similarly, for the two gauge, everything with 2s. The three gauge, everything with 3s. The Schrodinger gauge, everything with S's. Okay. To get to the one gauge, you just do a natural lift of the Laplacian on shape space. You do a natural lift of it to absolute configuration space. That's the one gauge. And the Hamiltonian H1 is basically proportional to that Laplacian. Delta 1, no potential. That's a very unfamiliar looking kind of dynamics from the absolute configuration space point of view. And it does not agree with what you might think it would be, namely the dynamics involving Laplacian, involving the Laplace-Beltrami operator associated with the invariant metric G, not on shape space, but the invariant metric on absolute configuration space. Delta 1 is not equal to delta G. You have to do some massaging, multiply psi1 by some suitable function to transform, to arrive at the two gauge where you do obtain a potential. And this is the gauge in which the Laplacian is the Laplace-Beltrami operator associated with the invariant metric on absolute configuration space, delta G. That also is a fairly unfamiliar kind of Laplacian. And it gives you a dynamics which is not self-adjoint with respect to the usual Lebesgue measure on absolute configurations. So it's a little bit unfamiliar from that point of view. A bit more massaging takes you to the gauge, the three gauge, where you have a more familiar kind of Laplacian, del dot del with the 1 over the invariant, 1 over the conformal factor in between. This is self-adjoint with respect to the Lebesgue measure, so it's a much more familiar kind of Laplacian. That's the three gauge, but it's still not the familiar Laplacian. To get to the familiar Laplacian, you need a bit more massaging, and you need to something like a wave function of the universe, which is not time dependent. And when you do that, you get to the Schrodinger gauge, involving more familiar looking kind of physics. Okay, so those are some quantum gauges. A bit more on what we can learn from relational physics. I've insisted for many, many years that fundamental physical theory has to involve some primitive ontology, what the theory is fundamentally about. This should be a primitive ontology of local beables in space and time. Local beables are things which assign some sort of value to each point in space and time. They are localized. If we're dealing with relational space, there is no such thing as what's at a point of space, a particular point of space. There is no absolute space to which to make sense of it. Nonetheless, I still consider the situation we have with relational configurations a perfectly good primitive ontology with sort of really good local beables in some generalized sense. But the lesson here is that you need to be flexible when you talk about your notion of local and primitive ontology, relational versus absolute. Here's another little lesson, or an example of the kind of freedom that you have with relational time. On the left, the equation on the left is more or less the usual guiding equation, J over rho. The equation on the right is simpler, than blue is simpler looking. If you were to ask, if you think that the fundamental theory should be as simple as possible, the form on the right is simpler. Those two forms, if you take relational time to a point of view, are absolutely equivalent. They define exactly the same relational physics. Because the only difference between what's on the right and what's on the left is a multiplication by psi star psi, a real scalar, a positive scalar. So the difference, so multiplying a vector field by a scalar, or dividing by multiply by psi star psi to get rid of it, which would convert you to the form on the right, that just corresponds to a random time change, which doesn't matter. Now, but the form on the left has some advantages. It has advantages with respect to the behavior of subsystems, the usual projective form. Why advantages with respect to the behavior of subsystems? Because, well, suppose we have a subsystem which has its wave function, and then it's a product in the actual wave function in the universe is a product of that with the wave function of the environment. So it's psi times some psi prime, product wave function. Psi system times psi environment. With the form on the left, the psi environment, if you're interested in the wave function of the system, the wave function of the environment is going to cancel. If you're interested in the behavior of the system, form on the right, it's not true. It'll be, if the behavior, subsystem behavior will look more complicated. So to get nice system behavior with projectivity, this form on the left is better, but from the fundamental point of view, the form on the right might be more appropriate. There's something a bit puzzling about that. The form on the right suggests a density with the random time change, a density rho equals psi squared becomes a density 1. You might think the density, what the density is fundamental to physics, and how can something, the form on the right be equivalent to the form on the left if they are associated with different probabilities? Well, I don't have time to get into that. It's also connected with the non-normalizability probabilities. I don't have time to get into that. I'll just give a quick answer to what these answers to the probability puzzles are. It's the difference between a probability distribution on configuration space rho, which naturally gives you a probability distribution over histories. Just take a probability distribution of a configuration space for each configuration and evolve it, and you get a history. The original probability distribution is the time zero configuration. That's to be distinguished from the rather boldish blue on the right, which is the probability distribution not over histories, but over unparametrized histories, paths in shape space, relational histories. What I said is more fundamental, something for which the distribution at time t makes no sense. So, and it's a distribution of time t is supposed to be psi squared. Psi squared should be problematical from a fundamental point of view. The configuration at time t makes no sense. If your relational thinking forces you to take p, the probable p on the right, the probability distribution on configuration space seriously, on path space seriously. And when you do that, what you find is that this object on the left, which is just based on fundamental considerations. There's no xt configuration at time here. There's just something, what the time is replaced by the some aspect of configuration of the environment, y. But when you ask, what is that really given by? It's given by familiar formula in terms of a wave function on absolute configurations, conditional wave function on absolute configuration space. No time to go into what the conditional wave function is. No time to go into more relational. All right, so let me just mention one further gauge. The quantum gauge, question mark, I don't know what it is, but that's actually what I'm looking for. Everything I've talked about so far, in the quantum case, the Bohmian quantum case, I started with a Bohmian motion on absolute configurations, on shape space. But the real goal was to start with something which is not Bowman, which is not quantum at all, no psi. The question is, where does psi come from? Suppose we have some motion on shape space, there's no psi in it involved. It doesn't come from, you can't even cast it into a form that involves a wave function psi. It's just not of that form. The natural motion you arrive at in shape space, so let's pretend the natural motion on shape space is not quantum at all. It doesn't look, there's no psi in it at all. But when you take into account the freedom of random time change, when you take into account the freedom of how you live, when you take into account all the gauge degrees of freedom, perhaps that gets transformed into a motion, which is a quantum motion involving wave functions. So that if that were the case, it would turn out that quantum mechanics, while entirely absent on the fundamental shape space level, arises as a choice of gauge on the absolute configuration space level. So with that, I stop and I thank you for your attention.
And thank you very much for the great talk. I'd say we take about 10 minutes for questions about your talk specifically, and then we slowly move into the general discussion and open it up. So again, if you have questions, please raise your hand. And Eddie, hi Eddie.
Hi Dusty, hi Shelley.
Hi, Eddie.
I can't see you, Shelley.
Oh, why is that?
Oh,
We were able to
Oh
see
yeah,
me.
I can see you now. All right.
Were you able to see me before?
Yes, yes. Okay, good. So Shelley,
Should
my
we
question
stop
is
the
about
screen? Sorry, should we
the
stop the
Kantian
screen sharing,
component.
or do you still need the slides?
I don't know. Depends on what the questions will be.
Okay.
Should I stop
Okay.
sharing? Okay, if I have to share again, I'll share again. Let's start. I'll stop the share.
Okay. So my question is this, Shelley, about the status of the gauge, say the Schrodinger gauge for the interaction and the quantum gauge in the eventual recovery of quantum theory from, say, classical shape space. Thinking here is a large Kantian component. You can think that this is entirely due to us. But would it be possible on this view to regard the choice of the gauge as something being specified by fundamental law of physics? That there's a law that specifies this is the correct gauge for this world, or this is the correct structure for motion, the correct interaction. But this law would have to be something connecting the fundamental shape space to the absolute configuration space in some way. And that might be a kind of weird law because it relates one fundamental stuff and the other being a non-fundamental stuff. But if there were a law, maybe someone who is less Kantian inclined would think that, okay, here is something that's out there in the world, is to be discovered by us. It's not up to us to specify what the world is like, or at least the structure of motion. Are you open to this option?
Well,
or is
if
that...
I were to, that sort of conflicts with a full relational point of view. From a full relational point of view, there's no room for there to be such a law. That would mean there's something beyond the shape space level, the relational level, which the relational physics leaves out. That's what you're referring to. So if you're going fully relational, that's just not a possibility.
But think of the law as not something in space-time or in shape space. It's like a constraint on motion.
But it's remember, from the relational point of view, these are not physical differences.
Right.
So the law was not concerned that your law would have nothing to do with anything with substantive physics. It would have to do with how we express the physics. I just don't see room. If from a fully relational point of view, I just don't see how that works. Look, there's an interesting question. There could be not laws, fundamental laws as you would like, but there could be some theorems which say, this way of lifting has these nice features. Some lifts are maybe better than others. Suppose one could do this quantum kind of lift that I'm talking about. And even though I left, it was just a question mark, since I don't know how to do it. If I knew how to do that, I would be really happy. Then I would really think I know where quantum mechanics is coming from. And then I would really understand something. And I would encourage young people to think about such questions, even though it could be not good for their careers. It won't hurt them in philosophy, though. There's a lot to think about. But one question is, okay, even if you can cast things in quantum form, you pick a gauge to put things in a more familiar form. A natural question is, well, why do we put it in that form? There are all these other forms. What's special about the familiar form? Well, one thing we know that's special about the familiar form is it is the form in which we ended up expressing stuff. Now, if we ended up expressing stuff that way, it's probably because there was something fairly natural about that form from our point of view. It became more natural to express it that way. I'm sure people must have looked at these questions and have some sort of done some quasi-systematic analysis. I certainly haven't done so, but there's lots of room for analysis about what kind of virtues you would have for choices of gauge. Why would you want to express physics in one versus another perfectly equivalent forms? What makes one form of expression better than another? What makes a quantum form of expression better than a non-quantum form of expression? Now, you probably know an answer to that, but one answer might be, let's say something like, something special about quantum mechanics is that you have statistical transparency, which makes it remarkably amazing simplification of the analysis of the consequence of the theory. Projectivity is another simplifying feature. But there's much more one could say.
Thank you, Shelley.
Zahant had a question.
Yeah, I had a question about the same point that Eddie just asked. Is that, I mean, you have in your mind a geodesic evolution of the actual shape of the universe. Yeah, you have the geodesic evolution on shape space, and you want to use this gauge freedom in lifting. And the question is, what brings you to this idea that with this freedom in gauge you could explain all the quantum phenomena? I mean, those are quite complicated.
Sahan, you're talking now about the classical case.
Yes, but you said that we don't have even in shape formulation of what you said. You don't have wave function on shape space. You said you just have a simple evolution of a shape.
No, I was saying what I would like. In most of what I talked about in the quantum case, I assumed quantum mechanics, Bohmian mechanics, on shape space, because shape space is a Riemannian manifold. I would say, from my point of view, that's not enough. I want to understand where quantum mechanics comes from. Where does the wave function come from? So I would like to have some compelling natural dynamics on shape space, which, when lifted appropriately and with an appropriate choice of time change, lifted appropriately, so an appropriate choice of gauge, you get something that looks quantum. That is quantum. I don't have that. I don't know that that can be done.
Yeah, my question was based on what you think that something like that along this line of argumentation could ever be found. I mean, you are starting with something that doesn't evolve any wave, just some evolution, some natural or beautiful evolution on shape space. And then at the end, you want to have some quantum mechanics which involves complicated wave function on absolute configuration space. I mean, if you can do that, or if somebody can do that, it's very nice derivation of the quantum mechanics. It's very beautiful, but the justification why you think this could lead to an answer, maybe you have some intuition. Can you explain?
I know I don't have a great intuition. I'm saying we have a lot of flexibility. It seems to me something like this must be true if quantum mechanics is correct. I'm putting it forward to you, young people, to think about. I can't do it. I don't know how to do it. It's not that I see any great obstacle, but I see it'll require a lot of work. I don't know how to do it.
Okay.
Maybe you can, Sahan.
We can talk about that. Yeah.
Paula has a question.
Okay, so hi, Shelley. I have a question. When you talk about the Newton gauge, you say that you get the potential, but then I guess you get the potential, which is not the Newton potential, but homogeneous of degree -2, so that it is scale invariant. Is that correct?
It has to be, yeah, right.
So it's quite a different series how you get out.
No, it's not exactly just Newton, but that had to do with the expansion gauge. I mean, you can do some stuff to get it a little bit better, and then do some further. Look, that's quite true, but that's a little bit far afield from my main concern, which is the quantum case. So that if things are not going right in the classical case, that's okay. I mean, I'm really trying. My main motivation is understanding quantum mechanics better, and exploiting the resources of shape space and the flexibility that shape space affords to get a handle on the question: who ordered that?
Yeah, I see what you're heading at.
Can I ask about that? Of course, it would be amazing if one could explain from first principle or principles, or at least more fundamental principles, how something like the wave function comes about. But I remember that not in the context of shape space, but just on standard configuration space, many people try to do it, somehow recover Schrödinger's equation from Madelung equations, or from the Bowman guiding equation, and kind of never worked. I don't remember exactly why.
Yeah, I don't think anything really serious has been done.
Mm-hmm. Okay, so but
even on absolute configuration space, but obviously one point I'm making here is you have many more resources if you go relational.
mm-hmm. I see. So that's the reason to be.
You have many more resources, and since relational, there are many virtues of being relational to begin with, right?
Mm-hmm. Right. And another short question: when you said if we're thinking about the wave function of the universe, there are reasons to believe that it's stationary and non-normalizable. Are you thinking of a Wheeler-DeWitt kind of setup?
For example, but I mean, I just have the feeling that now this is based on relativity and not. The general feeling is it just doesn't make a lot of sense for the wave function of the universe to be changing with time. I'm also thinking of it because, well, if it's a law, it shouldn't be changing with time.
Mm-hmm.
And non-normalizable, that seems to be, the non-normalizability of this wave function universe actually turns out to be a virtue. It's what enables the kind of probability formula I wrote down at the end. It's what enables, more to the point, it's what enables you in a straightforward way to extract from a non-normalizable stationary probability distribution, stationary under a flow, stationary probability distribution on a configuration space, a probability distribution on relational paths, unparameterized paths in the configuration space. What enables you to do that is having a normalizable wave function, or non-normalized wave function or probability distribution. So that non-normalizability from this point of view, from a more fundamental point of view, becomes a virtue.